All right, welcome. We are going to investigate two properties of random variables, the expected value and the variance in this video. And to motivate our exploration, we are going to consider the following scenario. We have two opportunities to win some money in a raffle. So in Raffle A, we have 10,000 tickets that are out in this raffle. And out of those 10,000 tickets, 1/4 or 2,500 of those tickets are going to win $10. And the other 3/4 of the tickets, they're not going to win any money. In Raffle B, there are also 10,000 tickets. 2 of the tickets win a $100 prize, and 1 ticket wins a grand prize of $25,000, and all the rest of the tickets do not win any money. So if you had the opportunity to get either raffle ticket A or raffle ticket B, which ticket would you prefer? Well, there's a lot to consider. For example, raffle A has a better chance of winning, but the amount that we win is much less compared to raffle B. So only 3 out of the 10,000 tickets here are going to win, but they're going to win a lot of money. So how can we quantify these distinctions and help us make an informed decision in this example? And so here we're looking at raffle tickets, but you can think of a lot of decisions that you make in life, in work, in your research in these terms. We think about what are the possible outcomes, how likely is each of those outcomes to occur, and we're going to use random variables to help organize this information. Okay, so recall the general definition for our random variable x is that random variable x is a map from a sample space into some subspace of the real numbers. So in this case, our sample space is going to be all of the 10,000 possible tickets in each of these raffles. We pick a ticket, and our random variable x is going to map that outcome to the amount of money that that ticket wins. So we're going to let random variable x denote the outcomes in raffle A. We're going to let random variable y denote the amount of money that a ticket wins from raffle B. And so organizing this information into what we call a probability mass function for random variable x, the possible values, the possible amounts that we could win are going to be no money. There's a 75% chance for that. Or we could win $10, and 1 out of 4 tickets, or a proportion of 0.25, is the probability of winning $10 on a raffle ticket. For raffle B, we have a different random variable, y, and the probability mass function for this random variable, we have 3 possible outcomes. We win no money, we win $100, or we win the grand prize of $25,000. So 1 out of 10,000 tickets has a chance of winning that grand prize. 2 out of 10,000 have a chance of winning the $100, and all of the rest, which is almost all of them, they are going to have they're not going to win any money, so they're 0. And recall just general properties of random variables, which are the sum of the probabilities need to add up to 1. They should account for 100% of the sample space. So here, adding up the probabilities gives us 1. Adding up the probabilities for the PMF of y also gives us 1. Okay, so now we have represented the payouts from raffle A with a random variable x, and we've got the PMF in this table over here. And for raffle B, we have random variable y representing the payoffs, which we have a second probability mass function. And one consideration that we can give is how much on average does a raffle ticket win? So what is the mean value of the random variable, in other words? Okay, so to calculate a mean, we're going to use the same old formula, which is we're going to add up all of the possible values of x and then divide by n. So in this case, x would be all 10,000 possible winnings for all 10,000 possible tickets. So we've got the first, say, 2,500 values in our sample would be the $10 that 25% of the people won, and the remaining 7,500 values in our sample would be all of the people that got $0. So we plug this information into our formula, say if we want to calculate the mean for random variable X, and we have 2,500 people that win $10, the 7,500 people that don't win any. We add up all these values and divide by 10,000, and we can group these values together as follows. So we can take the people that won $10 and add to it the people that won $0 and break up this fraction. So now we've got the 2,500 over 10,000. This is representing the proportion of people that won $10. And then we have the 7,500 over 10,000. This is representing the proportion of people that didn't win any money. And this gives us a sum that gives me 0.25 times 10 plus 0.75 times 0. And finally, calculating that gives us a mean of $2.50. So on average, a ticket is going to win $2.50 from lottery A for random variable X. And notice in this calculation, we have the product of the payoff of $10 times the probability that we would get a payoff of $10. And then we take this information to get this part of the sum, and this is telling me that the probability of winning $0 was 0.75. So we can make use of this general observation when we calculate the mean for random variable y. Namely, I'm going to just add up the sum of the products of each of these probabilities times the value y. So we have three different outcomes here, a payoff of 0, 100, or $25,000. So I'm going to have three pieces of this sum for the mean value for random variable y. So this is like the 0.01% chance of winning $25,000, the 2 out of 10,000 for winning 100, and all the rest of the people that don't win any money. And calculating this sum gives us a mean of $2.52. And so in this setting, the mean of these random variables is representing the amount that the ticket is expected to win. So for lottery A, a ticket is expected to win $2.50. In lottery B, a ticket is expected to win $2.52. But keep in mind, this is not a possible outcome for either of these raffles. So here, you're either going to win 0 or 10. And over here, it's not possible to win $2.52. So this is telling us the winnings on average. If you played this raffle 10,000 times, then on average, out of all of those 10,000 times, you would win an average of $2.50. So sometimes you win 0, sometimes you win 10. Averaging all of them out, you get $2.50 on average. Okay, so let's summarize the results from that previous slide. The expected value, here we're only working with discrete random variables. We'll see what happens with continuous random variables in class. But for a discrete random variable x, we denote the expected value with e of x. We can also use the mu sub x notation, and the expected value of random variable x is going to equal to all of the possible values of x times the probability of each of those values, and then we sum all of that together. And we can interpret this value as the average or mean value of random variable x. And in the case of the raffle, we had the expected value for a raffle ticket in raffle A was $2.50. The expected value for random variable y tells us how much we can expect to win in raffle B, which is $2.52. And again, just recall that this is telling us the average that we would get if we played these raffles over and over again many times, so that these expected values might not even be possible values that we can get from playing the raffle one time. And so if we're looking at these payoffs and we return back to our original question, which is which raffle ticket should we take, it seems like, well, raffle B, we can expect to win more, so we should choose raffle B. But there's more to consider here. So certainly on average, a person will win more in Raffle B. However, most of the time in Raffle B, you don't win any money. So in Raffle A, you've got a 25% chance of winning $10, whereas for Raffle B, you had a 99.97% chance of not winning any money. So your odds of winning money are better in Raffle A than they are in Raffle B. But Raffle B has one huge grand prize outlier. So the expected value that we got for Raffle B is going to be heavily influenced by that grand prize. And so as you consider which of these tickets you would prefer, you might want to think about, well, how much does that outlier factor into your decision process? And so weighing some of these other factors into consideration, we may want to explore other properties of these random variables that take things such as the variability of the winnings into consideration. Okay, so in addition to considering the expected value for tickets in each of these raffles, let's take into account now the variability. How much variability can we expect in the amount of money that we might win? And so one way that we've considered variability would be to calculate the average distance of values from the mean. So that would be a formula that would look like we're going to sum up all of the distances xi from the mean mu and then take the average and divide by n. But doing this formula is going to be problematic because some of our values are going to be less than the mean. They're going to have negative, the difference will be negative. Some of our values are going to be greater than the mean and they'll have a positive difference. And if we add them together, we're going to get cancellations between negative and positive values. So instead of just considering the average distance from the mean, we're going to think about the average squared distance from the mean. So therefore, positive and negative values aren't going to cancel each other out. And we denote this average squared distance from the mean with a sigma squared with a subscript, in this case x, referring to it is giving us the average squared distance from the mean of random variable x, which using the expected value notation, we can also think of as the mean or the expected value of the squared distance of x from its mean. So this might also be written in this form. Okay, so let's go ahead and calculate the average squared distance from the mean for random variable x. And so here we would start by taking the 10 minus the 250, since we're going to consider the outcome where we win $10. So that's squared distance from the mean, which was 250. And that's going to happen 25% of the time. So 2,500 out of the 10,000. And we're going to add to that the other distance from the mean. So we could win $0, and that's going to have a distance of 250 that we square. And we can rewrite this calculation in the following form. We can write it as 0.25, the probability of getting 10, times 10 minus 250 squared, where again the 250 is the expected value of x, plus the 0.75 probability associated to winning no money. So we're going to take 0.75 times the 0 minus 250 squared. And simplifying this calculation, we get 18.75. And we can repeat this calculation for random variable y, but now we're going to make use of this observation that we made when we were calculating this value for random variable x. So namely, this expected value of the average squared distance we can write as the sum over all possible values of y of the probability of y times the distance of y from the expected value squared. So that's exactly what we calculated over here. And so in the case of random variable y, we have three different possible outcomes. So we're going to have three pieces to this sum that I've written out. So this would be p of 25,000 times the distance from the mean. In this case, that's 2.52, plus p of 100 times 100 minus 2.52 squared, plus p of 0 times 0 minus 2.5 quantity squared. And simplifying that calculation, we get 62,495.65. So we can, comparing the variability, random variable y is way more variable than random variable x. And the units that we just calculated are squared. So this is not actually telling me dollars. The units that we're getting here are dollars squared. And so if we want to interpret these values, it's often nice to measure the variability in the same units as the random variable itself. So we can take the square root of this calculation to get the standard deviation, which in this case does have the same units of dollars. So the standard deviation for random variable x is $4.33 compared to the standard deviation for random variable y, which is approximately $250. And so taking all of this into consideration, both the expected value and the standard deviation, Raffle A, we're not expected to win as much money, but there's not a lot of variability here. So there's not as much of a chance of winning no money. We have a better chance of winning some money, just not a whole lot. For Raffle B, the expected value is a little bit more, but the variability is huge. So this is due to the fact that most of the time we don't win any money, but there's a very small chance of winning a huge amount of money. So taking both of these things into consideration would be useful before you decide which opportunity to take. Okay, so let's summarize the key points from this video. If we have a discrete random variable x, one useful property to consider is what's called the expected value, that we denote E of x or mu subscript x. And to calculate the expected value, we sum over all possible values of x times the probability of x. And in the end, this is going to tell us the average or the mean value of random variable x. We have also discussed ways of measuring the variability of a random variable. So this expected value of the squared distance from the mean, we call the variance of x. And we denote this with VARx or sigma squared x. So we use this Greek notation when we're describing properties of random variables. So the variance sigma squared x, in this case, we can calculate it by taking the squared distance from the mean times the probability of x and summing all of that together. And in class, we'll discuss some properties of the variance and maybe some shortcuts for calculating variance. But this would be the definition of how we calculate the variance. The variance is going to have different units from the variable x itself. So oftentimes we might describe the variability using the standard deviation, which is the square root of the variance, since that will have the same units as random variable x itself. And we denote the standard deviation with a sigma with a subscript of x. And for the standard deviation, we can essentially consider this as the average distance of values from the mean. And I say essentially because when we square something and take the square root, that's not exactly what we're getting, but pretty close. And the units of sigma x, again, are going to be the same as x. And so that's why the standard deviation is often a practical way to describe the spread instead of using the variance.